To start with, biomethane is the designation that we use to say that the methane produced comes from the a biological way. So the sources of production of the biogas that will be transformed into biomethane, it can be from the sewage treatment, and also there is biodigesters, especially designed for this purpose. But in the landfill, we can also collect and get the gases that are produced in the landfill and sent for purification. And in one of my latest videos, in the previous videos, I talked a little bit about the overview of the biomethane production from landfill, and now we will talk about specifically how to do the treatment and how to do the purification to get the biomethane. And the biomethane, of course, that it's a variable, reliable, not a reliable, but it's an energy source, so it's a good energy source, and in some manners it is renewable. So depending on the cost benefits, it can be a really interesting technology for countries that don't have too much gas available, or if the natural gas or if the methane is too expensive. Eventually, it's interesting to evaluate if the biomethane production is worth. And I hope that in this presentation you can get some kind of insights on how you can evaluate that. So there is an introduction here, and one thing that's important to understand and that impacts the technology that we will choose is the kinds of contaminants that you have in your biogas. So in general, when you have biogas from biological waste, biological production, the content of the methane varies from 50 to 70%, and that depends on the source of the biogas, if it is a biodigester with the organic material, or if we are talking about sewage, or if we are talking about landfills. By my experience, landfills, the biomethane content, it's around 55 to 60% in volume of methane. And the others gases that it has in this stream is the CO2. It is the main impurity or the main component that we must remove from the biogas to turn that in biomethane. But there are others also, as H2S, that we must remove in order to comply with the requirements and also to prevent damage in the equipment. And the reactions to the production of the biomethane is produce a gas saturated with water, so we need to remove water also from the components. But you can have other kinds of contamination like ammonia or siloxanes, and we must guarantee that at the final of the purification we match the requirements of the regulation of the contract or something like that. So we'll talk about it during this presentation. Here I have some sketch. So these are sketch from the production of the biogas from the digester, but we can extend the biodigester for the landfill or for the waste treatment, and it is the source of the biogas. And depending on the raw material that is inside here to the microorganisms to eat and to produce methane, we will have the different composition of the methane. And this biogas, it is used in two main different ways. One of them is the production of energy without too much treatment. So the biogas that goes from the landfill or from the biodigester, the water is removed, and sometimes they use a chiller to decrease the temperature of the water, and in a sharing tube heat exchanger, the biogas passes through the heat exchanger, and because the lower temperature, the water at the saturated point in the biogas condenses, and this water is removed. And the biogas with methane and also with the CO2 and with the siloxanes goes to the generator, and it is burnt, and it generates electrical power. So it is a way of using the biogas produced from landfills and bioproduction. And with that, the electricity is produced, and it can be used for heating and cooling and etc. But another way to use the biogas is treating that. So doing the biogas upgrading, we can produce the biomethane. And with the biomethane, we can also use for electricity, for heat and cold, but we can use that as fuel, because now instead of having around 50 to 70 percent in volume, we can reach around 99.5% or eventually more than that, depending on the technology that we choose. And taking a zoom in the kind of use that we have in this below one gas to energy process, we have the landfill. So we have the collections in the wells in the landfill. The gas goes to the compression, and we use a blower to do that. We don't need too much pressure to send it to generator, electrical generator. So diesel engines, electrical generator, and it is produce energy to send to the electrical grid. And I don't work with this kind of use. My company or the company that I work on, the interest of getting the biogas from the landfill is to produce the biomethane. So the process is a little bit different, and for us chemical process engineers is much more interesting, because we get the biomethane from the landfill, we compress that in a blower and send it to the treatment or to the upgrading in order to get the biomethane. And we need to have the pre-treatment depending on the kinds of contaminants that we have. We have the CO2 removal, and once we get the specification, it is the biomethane or the methane, because when we use that, it doesn't matter, the energy is the same. We send it for gas utilities, and eventually the industry can use that to production and for processing. And talking about biomethane, depending on the location, we have different regulations and the specification for that. So if you are in the Europe, the regulation is different than for biogas that is, or for biomethane that is in the US, that is different from the biomethane produced in Brazil. In this table, as I am doing a presentation for business located in Brazil, I got a extract of the ANP resolution 685 from 2017, and here I have the specification, or the minimum specification for my biomethane can be selling to the gas grids in northwest and southwest and south and center east of Brazil. So here we can see that there is some regulation related to the calorific power, and also the WOB index. So we need to comply with these requirements in order to be able to sell the biomethane. and we have the minimum content of methane, and eventually we can have ethane also, propane. And we are very interested when we are treating the biomethane or the biogas about the oxygen. There is a maximum limit for that, and the CO2 also, and the others, let's say the inerts, CO2 plus oxygen plus nitrogen cannot be higher than 10 moles. And I have a specification for sulfur and sulfur also, and the dew point. It's very important to comply with dew point, hydrocarbon dew points, lexanes, chlorides, fluorides, and it is the compilation of all the requirements that we must comply in Brazil. And as I told you, in other countries, you need to do the same. You need to evaluate what are the requirements in order that you can fit the best technology for the biomethane purification. And the main upgrading, when we talk about the upgrading of the biogas to biomethane, we are talking about the CO2 removal, because it is the second main component in the gas stream. And about pre-treatment, eventually we will remove what is the impurities not related to CO2. And depending on the kind of technology that we are using, the pre-treatment can be before removing the CO2, and of course that in this case it is pre-treatment, but also when we remove the CO2, depending on the contaminant, we need to do a post-treatment to remove the other impurities. So for the main impurities that we have in the biogas is the hydrogen sulfide, and it is very important to remove this before processing the CO2, processing the biogas to remove the CO2. We have water, so we need to remove water. We need to remove the siloxanes or silicon organic compounds. We need to remove the oxygen, the nitrogen, and we can have others. And when we are talking about the production of the biogas, to this process happens what the environment that the microorganisms is without oxygen, because for the reactions to the microorganisms do the reaction to produce the biogas, we cannot have oxygen. But if we are talking about landfill, for instance, once we do a negative pressure to keep out the biogas from the landfill, depending on the cover, the kind of cover or the quality of the cover of the landfill, air can impregnate through the landfill, and we can have as impurity in our biogas the oxygen, or most often the nitrogen, because depending on how far the leaking point is, the air goes through the landfill, but the amount of oxygen available in the air is consumed by the microorganism, and the nitrogen is inert. So if it gets to the biogas, it goes to our plant, and to reach the requirements related to nitrogen, it can be very difficult. So if we are talking about biomethane or biogas from landfill, it's very important that the source of production, that the landfill is very well designed and maintained. As important as the design of the landfill is also the maintenance or the operations of the landfill. And between the landfill and the biogas purification, it can be some 100 meters from one point to another, and it is very important also to verify if there is any kind of leakage in the pipeline through the landfill and the biomethane purification. in many cases, and the facilities that I've been following, the pipeline is the HPDE, so high density polyethylene. So it's a polymer that we use to transport the gas from a point to another, and we use that because as a polymer it is cheaper than using the stainless steel, for instance, because it is a gas that has CO2 with saturated water, so we can form carbon acids. And if we have the hydrogen sulfide with water, we can produce also, we can form also acids, because the decrease in the temperature will condensate water. So to the best material, or the cost benefits of using the high density polyethylene is the best one for the project that I've been working on. So it's a kind of interesting information to you follow. And talking about the desulfurization, there are some options to remove the hydrogen sulfide. One of them is using a catalytic bed, and this way, based on the content of the H2S available in the gas and based on the flow rate, the companies or the supplier or the chemical process engineer will do the sizing of the catalytic bed, in order that from time to time this bed will be saturated, because all the components that are inside of the vessel to transform the H2S to inorganic sulfur will be consumed, and time to time we need to replace the content of the vessel. And in some cases we use only one vessel, depending on how big is the flow, how big is the size of the plant, or eventually we use two beds, and while one is in operation, the other one is in standby. And once we need to isolate one bed for removing and replacing the content, the other one will be in line for operations. In this way, we don't need to stop the plant only for the replacement of the catalyst. But there are some other options, and one of them is the biological option. And I have in touch with a kind of system where we do the scrubbing of the gas with a solution, a caustic solution, where it goes for a bioreactor where we have special microorganisms to remove the H2S from the gas. So that is a little more complicated way of operating the plant, because if we are using chemicals, we know the behavior of the chemicals, and it is our starts for operations. But when we are talking about microorganisms, if for any reason you need to be a long period of time shut down your plant, you will not have a source or energy source to keep your microorganisms alive. So depending on the location, depending on the conditions, it can be an issue to restart the plant again. So this kind of evaluation depends on a series of factors. One of them, of course, is the capex, is the opex of the plant. And to evaluate what is the best one, you need to have the specification of your biogas. You need to know how much is the plant capacity, and etc. And another contaminant that we usually remove before sending the gas to the CO2 removal is the water. And there are many ways to remove the water. One of them is decrease the temperature, as I told you before. And in other cases, we need to use a dissolvent, because the required dew point at the at the based on the regulation is very, very low. It, in my case here in Brazil, it is minus 45 Celsius degree of dew point at 1:08 a.m. And every time that we are talking about the dew point, it is very, very important to fix the basis for the dew point. So in this case it is 1:08 a.m. But we have depending on the technology that we use, if we use, for instance, solvent, organic solvent, they remove also a little bit of water. If it's not too much, we cannot send free water to the CO2 removal, but the saturated water at the gas, depending on the amount that is available, it can be removed there. Before I talk about the purification of the biomethane, we have some other contaminants, as you told you. We have siloxanes and ammonia. And siloxanes, eventually we use carbon beds, carbon activated beds to remove that, or depending on the technology, if we are having a scrubbing, a water scrubbing, it is dissolved in the water. So that's why it is not in evidence in this presentation. And what I will share with you right now is the main technologies available to the purification of the biomethane. And when I'm talking about the purification, as I told you, is the removal of the CO2 from the methane, or from the biogas, that will turn from biogas to biomethane. And the main technologies available is the membrane separation, and we'll see some slides related to that. Is the scrubbing technologies, that is methods of absorption, and we have physical removal, we have chemical removal, and in the physical removal we have water used, and we have solvent uses, and we have also the pressure swing adsorption, and it is more known as PSA. And we have the cryogenic treatment, that is a way also to remove the CO2 from the biogas or from the biomethane. So we start with the membrane. What happens in the membrane is that the methods of separation principle is the diffusion of the gas through a polymer that is used as like a filter. And what happens here is that based on the different size of the molecules that is with the related to methane and CO2, the membrane is able to let the CO2 pass through the membranes, and the methane keeps inside, and with that we purify the gas with the membrane. But of course that there is some of the methane will also goes out with the CO2, and because of that we have a gas that is poor with methane, but there are some kinds of flammable in this waste stream. And an important thing to consider is that, as I told you, if we have nitrogen as a contaminant, we are not able to remove the nitrogen from the methane use membranes, because the size of the methane and nitrogen is very, very similar, and the suppliers are not able to remove the nitrogen use membranes. So it is a point of observation when we are looking for the technology for the purification of the biomethane. And what I just said is available here, and to increase the recovery of the methane use membranes is in many cases we need to use tube bundles that are connected in 2 stages or 3 stages, because the waste from a membrane will be compressed again to be sent to another one, or to do a recycle of the stream, and with that we can increase the capacity or the recovery of the methane in the system. And some advantage of using the membrane is that it doesn't have moving parts. You just need a source of building pressure, and remember that in the landfill or in the digester, the operating pressure is around the atmosphere. So to keep the gas, we need some kind of rotating equipment, and we use a blower in many cases to keep the gas and to build pressure enough to surpass all the pressure drop of the system. And talking about the membrane, most often it operates in a range of 7 to 20 bar, and because of that we need a blower, or in this case we need a compressor. So in this case, disconsidering the compressor, we don't have moving parts. You just need to have a gas with enough pressure to go in the membrane and to go out from the membrane. The availability depends on the compressor blower, because it's our source of capturing the biogas, and it can have a modular design. It means that if you want to increase the plant capacity, you just need to add more modules to your system, and with that you can improve the capacity of your plant. And in the other hand, we have some power requirements, and every kind of technology has some kind of power requirements. The methane losses can be between 0.5% to 12% in moles, and when we talk about volume, we can consider at moles also. And to decrease the methane losses, we will need to improve the methane design. You have more recirculation, have different stages of treatment, and etc. And now let's talk about the scrubbing technologies. The scrubbing technologies is when we use a solvent and we use a liquid to remove the CO2 from the biogas. And there are different techniques for that. As I told you, we can use a physical solvent, and in this case we can consider the water or organic solvent, and we can use also the chemical solvent, and in many cases we use amine, and the amine reacts with the CO2 to kept it from the biogas, and during the steps of regeneration we release the CO2 from the amine, and with that we can recirculate the amine again, and it is very, very similar with what we have in the hydration system. It's very, very similar. I will not talk about the amine system, but we'll talk a little bit about the water scrubbing and also the organic solvent. So what we have here is that the biogas goes into a tower, to absorber tower, and you can simulate absorber tower in the Eisenhower seas or in many process simulation software. And the absorber can be a tray tower, or it can be a package tower, and we send the water, sprays the water against the biogas. And because of the increase in the pressure of the system, the CO2 dissolves in the water, and it is very similar with what we have in the Coke, for instance, or in the soda. It is a pressurized liquid, and when we release the pressure from the bottle, the CO2 is starting degassing, starting dissolving from the liquid. And it is the same principle So at some pressure that can range from 4 to 10 bar G, the water will dissolve the CO2, and the water plus CO2 will go to a flash drum or a flash vessel, and in an intermediate pressure we can release the methane that is also absorbed during this process in the absorber. And we use the flash gas to recirculate to inside of our column in order that we can improve the recovery of the methane. And the water with the CO2 goes to a stripping column, and in this stripping column the objective is to release the CO2 from the water, and release other contaminants that are also dissolved in water. And it is very interesting, this kind of process, because if we have H2S, it is soluble in the water also, so we can remove the H2S, and the volatile organic compounds is soluble also, so we remove that, and we can use the air to do the stripping of the water and regenerate the water. And in terms of operations, we must monitor the pH of this water, and time to time we need to do the blowdown, or we have to have a blowdown continuously, because we are not able to remove 100% of the CO2 from the water. And to not saturate it and to not lose the quality of the gas, we need to renew the water. We need to add fresh water to the system, and because of that, this kind of technology has an intense water requirement. So if you are in a location that the water is very expensive, or if the water is not available, eventually it will not be the best kind of technology to you consider for your process. On the other hand, it is very simple operation. Technically it is relatively simple method, and you don't need to have a heat source for regenerate the water. You just need a blower to use air to remove the CO2. So there are some kinds of advantage. And in the other hand, the disadvantage is that the water is less selective than other solvents. So when we use the organic solvents, our target is to increase the performance and don't have this kind of worry about using water. And when you discharge the water you cannot not discharge the water for the river, for instance. You need to have some kind of pre-treatment to comply with the requirements. So this is some kind of issues that you must worry about when we are talking about water scrubbing. So guys, now let's talk about the organic scrubbing, and it is when we use a solvent to, instead of using water, we use a solvent to capture the CO2 from the biogas. And there are some kind of different commercial solvents available in the market. One of them is the Select Sol, and you can also simulate this in the Aspen high seas. And although there is no Select Sol component available there, you can use the DEPG component, because it has the same structure and it's very similar to the Select Sol, Organosorb, or something like that. So what happens here in the organic scrubbing is that we in this supply, okay, in this licensor, we have the first absorption column, and in this absorption column we will remove a small part of CO2 but we are interested in removing the remaining water and also the VOCs. So the select soil will capture them, and if there is a small content of the H2S, the select soil is also able to remove that. And we send to a stripping column where with the release of this stripping column is sent to an incinerator, and it goes to an incinerator because we have VOCs, we have H2S, and we cannot send to the flare because in the flare there is not enough energy to burn these components. So that's why we need to have an incinerator instead of a flare. And we have the recovery of the solvent, so we need to decrease its temperature. We can have some kind of makeup here, and we do recirculate that again to the absorber column to keep operating the plant at a closed loop. And the biogas with less content, without water and without VOCs goes to another column, and this time the amount of the select soil used to remove the CO2 is much higher. Just for references, for instance, here we are talking about 650 standard gallons per minute of select soil recirculation, while in this first part we are talking about only 12 standard gallons per minute. So you can see that the first stage of treatment, the objective is not to remove the CO2, is to remove the VOCs and the H2S and the water. And here, it's in this stage of purification, it's very similar to the water scrubbing. So the solvent with the CO2 goes to a flash tank, and with an intermediate pressure, we have a control valve here to control the level of the absorber, and this control valve is designed to add a higher pressure drop in the system in order that we can decrease the pressure, and with the decreasing of this pressure we release the some CO2 but also the methane that was captured in the solvent. And this methane we recirculate for the system. In this case we have a compressor, and the compressor gets this gas that is at lower pressure, increase the pressure, there is an air cooler in this case, and it re-injects at the inlet of the first column in order that we can improve the recovery of the methane in this process. And from the first depressurization, the select soil or the solvent goes to another depressurization, and this time it goes to a vessel that works at atmospheric pressure, and the CO2 is released from the solvent. And as it is CO2, you don't need to send it to flare, or you don't need to send that to atmosphere, to incinerator, because it was already it is in the inert form. This gas is already in the inert form. But to increase the recovery of the solvent, we have another stage of regeneration. In this case, we have a vessel under vacuum operation, and with that we remove more CO2 from the solvent. And in this case, we use this CO2 and other contaminants that we already have in the solvent. We use this as the gas, the stripping gas to our stripper. So you can see that we have a blower here because we are under vacuum operation, and we build some pressure just enough to be able to do the stripping of the first part of the solvent, and with that we regenerate the first stage of the solvent, and we have the second stage of the solvent regenerated also. And an interesting thing to note here in this process is that in the first part, we do the regeneration of the solvent, adding temperature, heating up the solvent to release the impurities from the solvent. And in the second part, we use a chiller to decrease the temperature of the solvent, and with that increase the performance to remove the CO2. And instead of using heating, we use the pressure to do the release and the recovery of the solvent. So in this way, we can get the purity that we want to in our product, in our biomethane, and we don't, as a solvent, we cannot discharge that to the ambient, to the environment. So, and we don't need to do that. What you need to make sure in terms of operations is time to time do a verification of the degradation of the solvent, because as it is a diethylene, diethyl glycol, it will not stand forever. Eventually you will need to replace that to improve your performance on the performance of the plant again. So it is similar to the water scrubbing, but depending on the design, it has more specificities, but it is very nice for us chemical process engineers. It is a kind of process very nice. And as I told you, you can simulate this in the Aspen-High-Seas. This simulation is the ProMax, but Aspen-High-Seas is also able to do this kind of simulation. I already did that, and eventually I will record a video specific to talk about the simulation of this process. So some advantage of the organic scrubbing is the high solubility of the solvent, so you can remove more CO2 from the biogas and lose less methane from your biogas. And there is the hydrophobic property of the solvent, you can produce a gas that is dried. Okay, so and some of the disadvantage is that, of course, that the solvent is not cheap, and it cannot be for release to environment, and you don't want that. You want to keep as much as possible in your process, and you will have a stream that must be burnt because legal regulation. We cannot send too much VOCs to atmosphere. We cannot send too much H2S to atmosphere. So we need to burn the gas from the stripping column. So this is some of the advantage. But for us that works with chemicals and petrochemical plants, that is very common to have some kind flare or some kind of incinerator to burn the chemicals that cannot be released in nature to the atmosphere. And another technology available to do the purification of the biogas to the biomethane is the pressure swing adsorption. And it is a method that uses the adsorption of the contaminants at the surface of a physical material. So depending on the type of the molecular sieve, or depending on the objective that we have, we use different kinds of material to remove the contaminants. The PSA is very used in air separation units when we need to remove the CO2 from air, and when we need to remove the heavy hydrocarbons from air in order to separate the nitrogen, the oxygen, and the argon. But there are another kind of adsorption process that is the TSA, and the TSA, instead of using pressure to do the regeneration of the molecules, the molecular sieve, we use temperature. And in some cases, we use temperature and the pressurization to do the regeneration. So the principle here is based on the different attraction of the adsorbent to the gas material. So the methane will pass through the bed, and the CO2 will be captured by the activated carbons, zeolitic, or carbon molecular sieve. And as we are talking about a process, it is a batch process, because we have a time, a predetermined or a calculated time that you can send the contaminated gas with the CO2 through the bed. And time to time, you need to switch the gas to another vessel, because if you don't do that, your vessel will be saturated and it will not remove CO2 anymore. And because of that, most often we have many vessels in parallel, while one is in operation, the other is in a regeneration step that can be the pressurization, equalization, or pressurization. And because of that, usually the PSA technology is more expensive than the others technology. Of course, that in the end is all a matter of the technical and economical evaluation, but you already know that usually it's more expensive. And the advantage of having the PSA is that it is a proven technology for sure. So there are places that works with PSA for many years without any issue. You don't have any kind of solvent that are needed to handle. You don't need to have pre-treatment to solvent, for instance, for water. You don't need to spend money with organic solvents, and that's an advantage. And as we are talking about pressure swing adsorption, we don't need any kind of source of heating to remove the impurities from the adsorbent. And in the other hand, we must remove the H2S before sending the gas to the PSA, because the H2S is not the adsolvent is not supposed to remove the H2S, and it can kill your molecular sieve or your adsolvent. And as we work with the depressurization, we eventually will have a waste gas. And to improve the recovery of the methane in this process, we also need to have a boosting system or a compressor to send the waste gas to the inlet of the process, in order that we can improve the capacity of the PSA. So that can increase the power requirements of your plant because of that. And finally, as technology is available, we have the cryogenic treatment. And among the technologies that we have seen up to this point, this one is the less used, and it is because it is very power demanding, because we need to do, the principle here is that we we can't condensate the streams based on different pressures and different temperatures, and we can liquefy the CO2 and keep the methane as the remove the methane as gas while we are liquefying the CO2. And with that, we can have a methane with a higher purity than compared to the other technology, because in this case, the methane is not liquefied, only the CO2 is liquefied. And of course that, as we are talking about very low temperatures, we cannot have water in this process, and so we must be aware of that. And I don't have too much details, but what you can see is that we choose the pressure and temperature conditions based on the differential condensation of the components. And now I will share with you more details about what we do as chemical process engineers once we are in the industry. Up to this point, we have discussed about the technologies available, but I'm only doing that because I have a purpose to do that. The company needs to has a biogas source, and I need to evaluate what is the best technology for selection, select the best technology for treat that biogas. And to do that, we need to prepare a technical specification in order to ask for quotations to suppliers. If you are in a company that builds this kind of process, you will receive from customers a specification informing the raw gas conditions, and depending on the raw gas conditions, you can apply one technology and cannot apply other. And also you need to know what is the product requirements in order to establish what is the best technology between having the product at the specification and the raw material that is available to you. You can see that it is part of a specification that I have done to do the quotation of the technology that we have been discussing up to this point. And what kind of information I have here? I need to define a tag for the system. In this case, I am interested in letting the supplier propose which kind of technologies best fits for these conditions. So it can be adsorption, can be absorption, can be permeate or PSA. Doesn't matter for me up to this point, because I will get all the quotations and I will compare them to evaluate what is best to the company. I need to inform what kind of operations is requested, if it's batch operation or if it's continuous. The service is for biomethane production, and my product requirements is the flow. I need to inform the flow to the supplier in order that they can size the equipments and the process. I need to inform the minimal pressure, because depending on the pressure available to the, in this case is the product requirements, depending on the pressure requirements and the pressure available to the raw gas, I will need to have a compressor or not. So it is very, very important information. And also the maximum temperature, because if we do heating, or if we in most cases, if we are applying heating to remove the CO2 from the biogas, we need to cool down that before sending it to the battery limits. So if we have some kind of requirements related to minimum temperature, we need to inform also the range that we can have in the product specification. All of this is very, very important when we are talking with the suppliers, or if you are receiving information to design this kind of process. And of course that we must know what is the composition requirements to the product, because based on that we'll do the process simulation and evaluate the sizing of the absorption column, how much solvent are needed to remove the CO2, or if we need to add activated carbon beds to remove the siloxanes, and etc. And all of these, the process is defined based on not only the product requirements, but also the raw gas conditions. So in this case, I have the raw gas flow available of 4,050 novel cubic meters, and the pressure, minimal pressure available is negative 100 millibar G, because in this case I already considered the distance between the landfill and my processing unit. So between the 2 points there is a pressure drop, and as the source of the gas is at atmosphere, it is 0 bar G. Once the fluid flow through the pipeline, there is the pressure drop, and I will have a negative pressure at my operating unit. So I already informed to the supplier which is the expected minimum pressure. And I informed also the maximum temperature that is expected, because once this process produces a biogas that is saturated with water, as higher is the temperature that I can reach here, higher will be the water content in my gas stream. So it is very, very important to inform and to consider during the process simulation and during the sizing of the equipment. And of course that I must inform the raw gas conditions or the composition. And what we can see here is that the methane requirements is 95.5% in volume, and we have as nitrogen around 6% in volume. So depending on the technology that I use, I will not be able to guarantee the requirements without nitrogen removal unit, because as you have seen, the membrane is not able to remove the nitrogen, because the size of the nitrogen is very similar to the methane. So it will accumulate at the product with the methane, and I will not be able to reach this purity. And the nitrogen, I cannot remove the nitrogen in the scrubber, and because the water or the solvent are not able to capturing the nitrogen, so it will accumulate also. And eventually I can remove the nitrogen if I use a PSA. And as I told you, the PSA usually is more expensive than the others technology. So it's a matter of economical evaluation to verify if it's better to have, for instance, organic scrubbing, and before the gas from the scrubbing, if I can use a nitrogen removal unit. And because of that we must do a specification and send for quotation with different suppliers in order to be able to evaluate this kind of issue. And here I share with you just some comparisons here that I did during the evaluation of this process. I removed the budget, how much it can be, or how much is the price or the capital cost for implementing this kind of technology. And what I can say to you is that for this range of raw gas treatment, it's around 7 millions to 10 millions or $1 million, okay? Only the purification unit. Remember that when we are talking about plant design, we are not talking about only about the process and the equipment. We are talking about also about civil engineering. We are talking about automation, and we are talking about utilities. So each kind of technology requires different kind of utilities, and it usually is not in the price of the supplier. For instance, if I need supply the water for this kind of process, the water will be OPEX, operation expenditure in my plant, and I must consider that during the evaluation of the economics. But in general, for what I would like that you observe here is that you must equalize all the quotation in order that you can evaluate which one is the best for your company. And you can see here that in this case, I don't have an equalization of my quotations because I have different compositions of raw gas, and this is this way because I got different quotations from different times. I also removed the time basis here just to not have any kind of issue with my company. And but I was able to build this chart in order just to have a sensing of how it will be with the quotation with my specific needs. So right now, what I'm doing is quotation specific for these requirements and gas composition. And once I have all the quotation, I will return to the chart and I will update the gas composition, and it will be the same for all technologies. I will evaluate the budget and the budgetary price for each technology. I need to evaluate the specific energy needed to produce the product, and usually it's kilowatts per hour for normal cubic meters of production in this case. One important thing, depending on the schedule of your project, is the time of fabrication of the technologies. Sometimes a process has a higher price than another one, but because of the schedule, I can anticipate the production. I can comply with the customer requirements sooner. It's best I pay a little bit more in the capex that waiting for a cheaper budget. And here I have listed the equipments, the main equipments that each technology includes. So in the PSA, I have a water chiller, feed blower, CO2 removal, biogas compressor, PSA vacuum pump, and etc. So this kind of evaluation is very, very common when we are talking about chemical process engineering in plant design. If you are working in an industrial plant, when you need to evaluate the options that you have to improve the capacity or to improve the performance of your plant, you will need to do this kind of evaluation in order to say to the management, okay, this is the best technology because of this and that, and because the price compared to the other ones is more, is less, the energy the specific energy is less, and something like that. So with this, I finished the presentation. Before I finish the presentation in itself, I use it as references the quotation that I have, and of course that is confidential to the company. But the main source of information to produce this presentation I got from the Biogas to Biomethane from the German Biogas Association. It's a publication from 2017, and the link to download this PDF is available here, but I will let this PDF available in my Telegram channel in process, and you can download that. You can download it from there, and it is not a copyrighted material. It's free for download from the German Biogas Association. So because of that, I will let available once I finish this presentation. I will let it available in my Telegram channel in process. If you don't know how to join my Telegram channel, the link is available in the description of this video in the YouTube, or you can find the link in my website, jeffersoncosta.com. This is it, guys. Thanks for being here, and see you soon in the next video. Bye bye.